Picture this, an invisible force lurking silently in the depths of space, holding entire galaxies together with a grip we can't see or touch. This mysterious presence makes up nearly 80% of all matter in the universe, yet it remains one of the biggest unsolved puzzles in science. We call it dark matter, and its secrets could rewrite everything we know about how the cosmos works. Now imagine standing on the edge of discovery, peering into a realm where the rules of physics bend and sometimes break. What if understanding dark matter could unlock answers to questions humanity has pondered for centuries? Questions like, how did the universe begin? Why does it look the way it does today? And what lies beyond the stars we see at night? In this video, we're diving deep into 25 mysteries surrounding the cosmic dark matter era. From strange gravitational effects to mind-bending theories about invisible particles, each revelation will challenge your perception of the universe. So buckle up, because by the time we're done, you'll have a whole new appreciation for the invisible forces shaping our reality and, just maybe, a glimpse into the future of space exploration. Keep watching to uncover the hidden truths behind the enigma of dark matter. Let's start our journey by unraveling the very essence of dark matter itself. At its core, dark matter is an invisible form of matter that doesn't emit, absorb, or reflect light, making it fundamentally different from everything we can see and touch. Despite this elusiveness, it plays a critical role in the universe, acting as the unseen scaffolding that holds galaxies together. Imagine trying to study something you can't observe directly. That's exactly the challenge scientists face when investigating dark matter. Unlike stars, planets, or even dust clouds, dark matter doesn't interact with electromagnetic forces, which means no telescopes can capture its glow or shadow. Instead, researchers rely on indirect evidence such as gravitational effects to infer its presence. For example, galaxies spin much faster than they should based on the visible matter alone. This discrepancy suggests there's far more mass out there than meets the eye, and that extra mass is dark matter. But why has detecting dark matter proven so difficult? Part of the reason lies in its properties. Scientists believe dark matter consists of particles that rarely collide with ordinary matter, making them nearly impossible to spot using traditional methods. Experiments deep underground in space and at particle accelerators aim to catch glimpses of these elusive particles, but success has been fleeting. As we continue to refine our tools and techniques, the hunt for direct detection remains one of the most exciting frontiers in modern science. Understanding dark matter isn't just about solving a cosmic puzzle, it's about uncovering the fundamental building blocks of reality. By delving deeper into its nature, we may unlock secrets about how the universe formed and evolved over billions of years. And that brings us closer to answering some of humanity's oldest questions. But before we move forward, let's take a closer look at another fascinating aspect: how dark matter influences galaxy rotation in ways that defy conventional physics. Shifting our focus now, let's dive into one of the most intriguing phenomena linked to dark matter: galaxy rotation anomalies. When astronomers first observed galaxies in detail, they noticed something peculiar. The stars and gas within these massive cosmic structures were moving much faster than expected based on the amount of visible matter present. This observation defied the predictions of classical physics, sparking a scientific mystery that continues to captivate researchers today. To understand why this is so surprising, consider the forces at play. In a typical solar system, planets orbit the sun because of gravity, with their speed decreasing as they move farther away from its center. However, when scientists applied this same logic to galaxies, expecting stars near the edges to move slower, they found just the opposite. Stars located far from the galactic center travel almost as quickly as those closer in, suggesting there's additional unseen mass influencing their motion. This invisible mass, that's where dark matter comes in. Scientists believe that vast halos of dark matter surround galaxies, providing the extra gravitational pull needed to explain these high-speed rotations. Without dark matter, galaxies would simply fly apart due to the centrifugal force caused by their rapid spinning. It's like an invisible glue holding everything together. But how do we know it's not just regular matter hiding somewhere? Extensive studies have shown that even accounting for all possible forms of ordinary matter, like dim stars, black holes, or interstellar dust, there still isn't enough mass to account for what we observe. Dark matter offers the most plausible explanation, bridging the gap between theory and observation. Exploring galaxy rotation anomalies gives us valuable insights into the distribution and behavior of dark matter across the universe. These findings don't just reshape our understanding of individual galaxies, they also challenge existing models of cosmology, pushing us toward new discoveries about the cosmos itself. With each step forward, we edge closer to unraveling the true nature of this mysterious substance. Moving beyond the intriguing world of galaxy rotation anomalies, let's now turn our attention to one of the most visually stunning aspects of the cosmos, the large-scale structure formation. This cosmic web, as it's often called, reveals an intricate pattern of galaxies, filaments, and vast empty spaces known as voids. At the heart of this phenomenon lies dark matter, acting as the unseen architect shaping the universe's grand design. Imagine the early universe as a dense, uniform sea of particles. As it expanded and cooled, tiny fluctuations in density emerged, creating regions slightly denser than others. These areas became gravitational attractors, pulling in surrounding matter. However, ordinary matter alone couldn't account for the rapid collapse and clustering observed today. Enter dark matter. Its presence provided the extra gravitational pull necessary to accelerate the formation of these massive structures. Dark matter doesn't interact with light or electromagnetic forces, but its gravity is unmatched. It formed the initial scaffolding upon which visible matter could gather. Over billions of years, this invisible framework guided the growth of galaxy filaments, long strands of galaxies stretching across millions of light years, and carved out enormous voids where almost no galaxies exist. The result, a breathtaking cosmic web that stretches across the observable universe. But how do scientists study something so elusive? Through computer simulations and observations of distant galaxies, researchers have pieced together a clearer picture of dark matter's role. By mapping the distribution of galaxies and analyzing their motions, they've discovered that dark matter halos serve as the foundation for all cosmic structures. Without dark matter, the universe would lack the rich tapestry of galaxies, clusters, and superclusters we see today. Understanding large-scale structure formation not only deepens our appreciation of the universe's beauty, but also sheds light on the fundamental properties of dark matter itself. Each filament and void represents a clue in the ongoing quest to unravel the mysteries of this enigmatic substance. As we continue exploring, the cosmic web remains both a testament to dark matter's influence and a tantalizing puzzle waiting to be solved. Shifting our focus now to another fascinating aspect of dark matter, let's explore gravitational lensing, a phenomenon that provides some of the most compelling evidence for its existence. Imagine light traveling across vast cosmic distances, only to be subtly bent as it passes near massive objects like galaxies or galaxy clusters. This bending of light, first predicted by Einstein's theory of general relativity, is known as gravitational lensing. But what makes this process particularly intriguing is how dark matter plays a starring role in amplifying these effects. Gravitational lensing occurs because mass, whether visible or invisible, warps spacetime around it. When light from distant stars or galaxies travels through regions rich in dark matter, the additional gravitational pull causes the light to follow curved paths. As a result, we observe distorted images of those distant objects here on Earth. Sometimes these distortions create multiple images of the same object, while other times they stretch and magnify them into arcs or rings, forming what astronomers call Einstein rings. This effect serves as a powerful tool for mapping dark matter distributions. By studying how light bends around galaxy clusters, scientists can infer where dark matter concentrations lie. For instance, observations reveal that certain areas exhibit stronger lensing effects than expected based solely on visible matter. These discrepancies highlight the presence of significant amounts of unseen dark matter influencing the region's gravity. There are two primary types of gravitational lensing: strong lensing and weak lensing. Strong lensing produces dramatic visual effects such as multiple images or bright arcs, often seen in stunning telescope photographs. Weak lensing, on the other hand, creates subtle distortions that require statistical analysis to detect. Both forms contribute valuable insights into the distribution and behavior of dark matter throughout the universe. One remarkable example comes from the Bullet Cluster, a collision between two massive galaxy clusters. Observations show that the visible matter, primarily hot gas, has been separated from the bulk of the mass due to the violent impact. Yet, gravitational lensing measurements indicate that the majority of the mass resides outside the visible gas clouds, aligning perfectly with dark matter predictions. Such findings reinforce the critical role dark matter plays in shaping the cosmos. Through gravitational lensing, researchers continue unlocking secrets about dark matter's elusive nature. Each new observation brings us closer to understanding this mysterious substance that dominates the universe yet remains so profoundly hidden from direct detection. Moving on to another captivating mystery of the cosmic dark matter era, let's delve into the enigmatic world of the cosmic microwave background, or CMB. This faint glow of radiation, a relic from the universe's infancy, holds crucial clues about the early interactions involving dark matter. The CMB is essentially a snapshot of the universe when it was just 380,000 years old, showcasing the first light that traveled freely through space. While this radiation appears nearly uniform across the sky, closer inspection reveals subtle irregularities, tiny temperature fluctuations, and variations in polarization patterns. These anomalies might seem insignificant at first glance, but they offer profound insights into the role dark matter played during the universe's earliest moments. One key aspect involves how dark matter influenced the distribution of ordinary matter before and after the CMB was emitted. Theoretical models suggest that dark matter's gravitational pull helped shape the density variation seen in the CMB. By studying these imprints, scientists can infer properties such as the total amount of dark matter present and its potential interactions with other forms of energy and matter. For instance, certain anomalies hint at the possibility of dark matter particles decaying or interacting with themselves shortly after the Big Bang. Such processes could have left distinct signatures in the CMB, altering the observed temperature fluctuations. Researchers are actively analyzing data from telescopes like Planck and WMAP to uncover these elusive traces, which may reveal whether dark matter behaved differently in the early universe compared to today. Moreover, the CMB also sheds light on the interplay between dark matter and neutrinos, another mysterious component of the cosmos. Evidence suggests that their combined effects might explain some of the peculiar features detected in the radiation spectrum. Understanding these connections brings us one step closer to unraveling the true nature of dark matter and its influence on the universe's evolution. Through the lens of the cosmic microwave background, we gain an extraordinary window into the past, allowing us to piece together the puzzle of dark matter's origins and behavior. Each new discovery adds layers of complexity and wonder to our understanding of this cosmic enigma. Shifting our focus to another intriguing aspect of the cosmic dark matter era, let's explore the mystery of missing baryonic matter. This discrepancy highlights a fundamental challenge in our understanding of the universe. there simply isn't enough visible matter to account for what theoretical models predict. Baryonic matter refers to ordinary matter made up of protons and neutrons, which constitute stars, planets, galaxies, and everything we can observe directly. However, when astronomers compare the amount of baryonic matter they detect with predictions from cosmological models, a significant portion seems to be unaccounted for. This so-called missing baryonic matter doesn't mean it vanished into thin air. It likely resides in hidden reservoirs that are difficult to observe. One leading hypothesis suggests that much of this missing matter exists in the form of warm hot intergalactic medium, or WIM. This diffuse gas fills vast regions between galaxies, heated to extreme temperatures by processes like shockwaves from galaxy formation and supernova explosions. Because WIM emits very faint X-ray radiation, detecting it requires highly sensitive instruments and sophisticated observational techniques. Another possibility involves dark matter playing a role in shielding or influencing these hidden reservoirs of baryonic matter. The gravitational pull of dark matter halos surrounding galaxies may confine this elusive material within their vast structures, making it harder to detect. Some researchers even speculate about interactions between dark matter and ordinary matter that could alter the distribution of baryons on large scales. Understanding the fate of missing baryonic matter not only tests our knowledge of cosmic structure, but also sheds light on how dark matter interacts with the visible universe. As scientists continue refining observations and simulations, each clue brings us closer to solving this puzzle. By piecing together evidence from various sources, we edge nearer to uncovering the full story of both dark and luminous components shaping our cosmos. Transitioning from the enigma of missing baryonic matter, let's now turn our attention to another fascinating aspect of the cosmic dark matter era, the peculiar dynamics of dwarf galaxies. These relatively small galaxies offer a unique window into the elusive nature of dark matter and its profound influence on galactic structures. Dwarf galaxies are characterized by their diminutive size compared to larger counterparts like our Milky Way. However, what they lack in scale, they make up for in intrigue. Observations reveal that stars within these galaxies move at velocities far exceeding what would be expected based solely on the gravitational pull of visible matter. This discrepancy strongly suggests the presence of unseen dark matter halos enveloping these celestial bodies. The concept of dark matter halos is crucial here. Scientists propose that vast amounts of dark matter surround dwarf galaxies, exerting significant gravitational forces that shape their structure and motion. In essence, these halos act as invisible scaffolding, providing the necessary mass to account for the observed stellar motions. Without this additional mass, the stars within dwarf galaxies would simply fly apart due to their high speeds. Moreover, the distribution and density profiles of these dark matter halos play a critical role in determining the internal dynamics of dwarf galaxies. Simulations suggest that the interaction between dark matter and baryonic matter within these systems can lead to complex behaviors, such as enhanced star formation rates or unusual orbital patterns. Such phenomena challenge existing models and prompt further investigation into the intricate relationship between dark matter and galaxy evolution. Understanding the dynamics of dwarf galaxies not only deepens our knowledge of dark matter, but also sheds light on the broader processes governing the formation and development of all galaxies. As researchers refine observational techniques and computational models, every new discovery brings us closer to unraveling the mysteries concealed within these cosmic marvels. By examining how dark matter shapes the smallest galaxies in the universe, we gain invaluable insights into the fundamental forces driving the cosmos. Shifting our focus from the dynamics of dwarf galaxies, let us now explore two leading candidates in the search for dark matter particles: Axions and weakly interacting massive particles, or WIMP. These hypothetical entities represent some of the most promising solutions to the cosmic mystery of dark matter, each with distinct characteristics and implications. Axions are theorized to be extremely lightweight particles that could have formed in abundance during the early universe. Unlike many other particles, axions possess properties that allow them to interact very weakly with ordinary matter and radiation, making them nearly invisible yet potentially ubiquitous throughout the cosmos. Their existence was initially proposed to resolve an issue in quantum chromodynamics, the theory describing the strong force that binds atomic nuclei together. If confirmed, axions could not only explain dark matter but also provide insights into fundamental physics beyond the standard model. On the other hand, WIMP, weakly interacting massive particles, are believed to be much heavier than axions with masses comparable to those of atomic nuclei. As their name suggests, these particles interact only through gravity and the weak nuclear force, rendering them elusive to detection by conventional means. However, their potential ability to annihilate with one another upon collision offers a tantalizing possibility for indirect observation. Such annihilation processes might produce detectable gamma rays or other high-energy particles, providing clues about the nature of dark matter. Both axions and WIMP share the common trait of being non-baryonic, meaning they do not consist of protons and neutrons like familiar forms of matter. This feature aligns well with observations suggesting that dark matter constitutes approximately 85% of all matter in the universe, far exceeding the amount of visible baryonic matter. Scientists worldwide are actively pursuing experiments designed to capture direct evidence of either particle type, employing advanced detectors deep underground or aboard orbiting observatories. The hunt for axions and WIMP continues to captivate researchers as it holds the key to unlocking one of the greatest puzzles in modern astrophysics. By understanding these enigmatic particles, we may finally bridge the gap between what we see in the heavens and the unseen forces shaping the fabric of reality itself. Moving our exploration further back in time, let us now journey to the very dawn of the cosmos and examine how phase transitions in the early universe may have shaped the nature of dark matter as we know it today. In the first fractions of a second after the Big Bang, the universe underwent dramatic transformations with fundamental forces separating from one another and particles coalescing out of pure energy. These phase transitions were pivotal moments that determined the structure and composition of everything that followed. During these transitions, conditions in the early universe were extreme, with temperatures and densities far surpassing anything we can replicate on Earth. It is within this chaotic environment that scientists theorize dark matter might have taken its form. One intriguing possibility is that dark matter particles emerged directly from these phase changes, born alongside familiar particles like quarks and electrons. Alternatively, some models suggest that dark matter could have originated indirectly through interactions with other particles during these transitions. Understanding these processes requires delving into the interplay between quantum mechanics and cosmology. For instance, certain theories propose that dark matter's properties are tied to symmetries broken during specific phase transitions. If such symmetries were disrupted, it could explain why dark matter behaves so differently from ordinary matter, interacting only minimally with the rest of the universe. Experimental efforts aim to recreate conditions similar to those in the early universe using particle accelerators, providing glimpses into what occurred during these critical moments. While these experiments face immense challenges, they offer hope for unraveling the origins of dark matter and shedding light on its role in shaping cosmic history. By piecing together this puzzle, we edge closer to comprehending not just dark matter, but also the fundamental laws governing our universe. As we continue exploring these ideas, the next mystery invites us to investigate the properties of dark matter halos surrounding galaxies, revealing yet another layer of intrigue in this cosmic saga. Shifting our focus now to the vast, invisible cocoons that cradle galaxies, let's explore the fascinating properties of dark matter halos. These mysterious structures surround galaxies like protective shields, influencing their growth and evolution over billions of years. But what exactly are these halos, and how do they shape the universe as we see it? Dark matter halos are immense clouds of non-luminous material that envelop galaxies, extending far beyond the visible boundaries of stars and gas. Their size, shape, and density vary depending on the galaxy they enclose, but one thing is certain: they play a crucial role in determining a galaxy's fate. For instance, larger halos tend to host more massive galaxies, while smaller ones correspond to dwarf galaxies. This relationship hints at an intricate dance between dark matter and ordinary matter throughout cosmic history. The structure of a dark matter halo isn't uniform. Instead, it features distinct regions with varying densities. At its core, the halo exhibits higher concentrations of dark matter, gradually thinning out toward its edges. Scientists study these profiles using sophisticated computer simulations and observations of gravitational effects, such as lensing. By analyzing how light bends around distant galaxies, researchers can infer the distribution of dark matter within their halos. But why does the shape of a halo matter? It turns out that the geometry of a dark matter halo reflects the conditions under which it formed. Some halos appear nearly spherical, while others take on elongated or flattened forms. These variations suggest differences in the environments where galaxies emerged, offering clues about the early universe's structure and dynamics. Understanding galactic halo properties also helps explain phenomena like galaxy mergers and star formation rates. When two galaxies collide, their dark matter halos interact first, influencing the outcome of the merger. Similarly, the presence of a dense halo can enhance star formation by stabilizing gas clouds against dispersal. As we continue probing the secrets of dark matter halos, each discovery brings us closer to unraveling the grand design of the cosmos. With advanced telescopes and computational tools, scientists are steadily piecing together this cosmic puzzle, revealing just how deeply intertwined dark matter is with the life cycles of galaxies. Moving beyond the structure of dark matter halos, let's now venture into the realm of indirect evidence for dark matter's presence, specifically the tantalizing possibility of dark matter annihilation signals. Imagine this: throughout the universe, dark matter particles might be colliding with one another, annihilating in a burst of energy and producing detectable byproducts such as gamma rays or high-energy particles. This concept opens up an exciting avenue for scientists to uncover the nature of dark matter without directly observing it. When dark matter particles meet under certain conditions, they could destroy each other, releasing a cascade of particles that include photons, neutrinos, or even antimatter. These remnants can travel vast distances and eventually reach Earth, where sensitive instruments are waiting to capture them. Gamma rays, in particular, stand out as a key indicator because they carry specific energy signatures that point back to their origin. By studying these signals, researchers aim to decode the properties of dark matter, including its mass and interaction rates. Several experiments around the globe are dedicated to detecting these elusive annihilation products. Space-based observatories like the Fermi Gamma Ray Space Telescope have already provided intriguing hints of potential dark matter annihilation in regions rich with dark matter, such as the centers of galaxies or galaxy clusters. Ground-based detectors also play a crucial role, searching for related phenomena such as excess positrons or antiprotons in cosmic rays. However, interpreting these signals is no simple task. Many astrophysical processes produce similar emissions, making it challenging to distinguish genuine dark matter annihilation from background noise. To address this, scientists rely on detailed models of dark matter behavior and cross-check observations against theoretical predictions. The quest continues, fueled by advancements in technology and growing datasets that bring us closer to confirming or ruling out this fascinating hypothesis. Understanding dark matter annihilation not only deepens our grasp of fundamental physics, but also sheds light on the universe's hidden architecture. With every new observation, we edge closer to solving one of cosmology's greatest puzzles. Let's shift gears now and explore an intriguing alternative to the particle-based explanations of dark matter: modified gravity theories. Instead of assuming that dark matter consists of undiscovered particles, these models propose that our understanding of gravity itself might need revision. Two prominent contenders in this field are modified Newtonian dynamics, or MND, and tensor vector scalar gravity, known as TVS. MND challenges the conventional view by suggesting that the laws of gravity behave differently at extremely low accelerations, such as those found in the outskirts of galaxies. In this framework, the observed gravitational effects attributed to dark matter could simply arise from a modification of how gravity operates under certain conditions. By tweaking the relationship between mass and force at large scales, MND successfully explains phenomena like galaxy rotation curves without requiring additional unseen matter. TVS takes this idea further by incorporating relativistic principles into the equation. Building on MND foundation, TVS introduces extra fields alongside the traditional gravitational field, creating a more comprehensive theory that aligns with Einstein's general relativity. This approach not only addresses issues within galactic dynamics, but also attempts to reconcile observations of cosmic expansion and structure formation. While both theories offer compelling alternatives to traditional dark matter models, they face significant challenges. For instance, neither fully accounts for all observed phenomena, such as the behavior of galaxy clusters or the distribution of matter revealed through gravitational lensing. Additionally, many physicists argue that modifying gravity raises its own set of complexities and unanswered questions about the fundamental nature of spacetime. Despite these limitations, modified gravity theories continue to inspire debate and exploration in the scientific community. They encourage us to question whether the mysteries of dark matter might be resolved not by discovering new particles, but by rethinking one of the most fundamental forces in the universe, gravity itself. As research progresses, these ideas remain valuable tools for expanding our understanding of the cosmos. Supermassive black holes at the centers of galaxies are among the most enigmatic and powerful objects in the universe. Now let's delve into a fascinating possibility. Could dark matter have played a crucial role in their formation? This idea challenges traditional theories that rely solely on baryonic matter collapsing to form these cosmic behemoths. In standard astrophysical models, supermassive black holes grow over billions of years through processes like accretion and mergers. However, observations suggest some of these giants existed remarkably early in the universe's history, raising questions about how they formed so quickly. Enter dark matter, a potential missing piece of this puzzle. Some researchers propose that dense concentrations of dark matter might have acted as seeds for these massive structures. Imagine regions in the early universe where dark matter clumped together due to gravitational attraction. These halos of dark matter could create deep gravitational wells, drawing in surrounding gas and dust with incredible efficiency. Over time, this process may have triggered the collapse of material into black holes far larger than those formed from stars alone. In fact, certain types of dark matter candidates, such as primordial black holes or ultra-compact minihalos, could directly contribute to the seeding process. Another intriguing theory involves fuzzy dark matter, which consists of extremely light particles behaving more like waves than particles under certain conditions. If present in sufficient quantities, fuzzy dark matter could stabilize massive objects against fragmentation during their early stages, allowing them to grow into supermassive black holes without breaking apart prematurely. While still speculative, this connection between dark matter and supermassive black hole formation opens exciting avenues for research. By studying the interplay between dark matter distributions and galactic evolution, scientists hope to uncover new clues about both phenomena. As we continue exploring this mystery, one thing becomes clear. The relationship between dark matter and black holes is far deeper and more complex than initially thought. Shifting our focus to another intriguing aspect of the cosmic dark matter era, let's explore the mysterious world of ultra-diffuse galaxies. These faint, sprawling structures challenge conventional notions of galaxy formation and dynamics, offering a unique window into the behavior of dark matter. Ultra-diffuse galaxies, or UDG, are among the most dimly lit galaxies in the universe. Unlike typical galaxies, they spread their stars thinly across vast regions, making them appear ghostly and nearly invisible against the night sky. What makes these galaxies particularly fascinating is their unusually high ratio of dark matter to visible matter. In fact, some UDGs contain up to 1,000 times more dark matter than ordinary galaxies of similar size. This extreme imbalance raises profound questions about how such systems form and survive over cosmic timescales. One prevailing theory suggests that ultra-diffuse galaxies may have formed in environments where dark matter played an outsized role from the very beginning. The immense gravitational influence of dark matter halos could have slowed down the collapse of gas clouds, preventing the rapid formation of dense star clusters. Instead, the material stretched out over larger areas, resulting in the diffuse structure we observe today. Another possibility involves tidal forces acting on smaller galaxies as they interact with neighboring giants, stripping away much of their stellar content while leaving behind the underlying dark matter framework. What truly sets ultra-diffuse galaxies apart is their potential to act as natural laboratories for studying dark matter. Since these galaxies contain so little visible matter, any observable effects, such as gravitational interactions or rotational patterns, are likely dominated by dark matter alone. By analyzing the motion of stars within UDGs, scientists hope to gain insights into the nature of dark matter particles and test competing theories about their properties. The study of ultra-diffuse galaxies also sheds light on broader questions about galactic evolution. For instance, why do some galaxies evolve into compact, star-filled disks while others remain sparse and scattered? Understanding the role of dark matter in shaping these diverse outcomes could unlock new secrets about the universe's history and structure. As research continues, ultra-diffuse galaxies stand as a testament to the complexity and mystery of the cosmos, inviting us to delve deeper into the enigmatic realm of dark matter. Venturing further into the intricate web of dark matter, let's now uncover the fascinating world of dark matter substructure. Imagine a universe where even the vast halos of dark matter surrounding galaxies are not uniform but instead host smaller clumps and concentrations within them. These small-scale structures, often referred to as subhalos, play a critical role in shaping the dynamics of galaxies and influencing processes like galaxy mergers and star formation. Subhalos are essentially miniature versions of dark matter halos, embedded within the larger ones that encircle galaxies. Their presence can have profound effects on the galaxies they inhabit. For example, when two galaxies collide or merge, the gravitational influence of these subhalos can significantly alter the outcome. They act as invisible yet powerful forces, pulling and tugging at the visible matter, affecting how stars and gas clouds interact during such cosmic events. Moreover, the existence of dark matter substructures has intriguing implications for star formation. In some cases, the dense concentration of dark matter in subhalos may enhance the gravitational pull on nearby gas clouds, triggering the collapse of these clouds and leading to bursts of star formation. Conversely, in other scenarios, the disruptive influence of subhalos might prevent gas from settling into stable configurations necessary for star birth, thereby suppressing star formation rates in certain regions of a galaxy. Understanding dark matter substructure is not only crucial for deciphering galaxy evolution, but also provides valuable insights into the nature of dark matter itself. The distribution and behavior of these subhalos could reveal clues about whether dark matter particles interact with each other or if they remain entirely collisionless, as current models suggest. Observations of galaxy mergers and detailed simulations of dark matter dynamics are helping scientists piece together this complex puzzle. As we continue to explore the hidden architecture of the cosmos, the study of dark matter substructure offers a promising avenue for unraveling some of the universe's deepest secrets. By examining the subtle yet significant impact of these small-scale structures, we gain a clearer picture of how galaxies form, evolve, and interact over billions of years. This exploration not only enriches our understanding of dark matter, but also deepens our appreciation for the intricate choreography of the universe. Shifting our focus now to another intriguing aspect of the cosmic dark matter era, let's explore the potential interactions between neutrinos and dark matter particles. Neutrinos, often called ghost particles due to their elusive nature, are among the most abundant yet least understood particles in the universe. While they interact very weakly with ordinary matter, recent theoretical models suggest that their connection to dark matter could hold profound implications for both fields. Imagine a scenario where neutrinos, traveling through vast expanses of space, occasionally collide with dark matter particles. These interactions, though rare, might leave detectable signatures that could provide clues about the properties of dark matter. Some theories propose that neutrinos could scatter off dark matter, transferring energy in the process. This subtle exchange might influence the behavior of dark matter on small scales, such as within galaxy halos or subhalos, offering indirect evidence of these mysterious particles. Moreover, certain models suggest that neutrinos might even transform into dark matter particles under specific conditions. This hypothetical phenomenon, known as neutrino oscillation into dark matter, could explain discrepancies observed in cosmic data. For instance, anomalies in the distribution of dark matter in certain galaxies might be attributed to such transformations, providing a new lens through which scientists can interpret existing observations. The study of neutrino-dark matter interactions also opens up exciting possibilities for experimental detection. Advanced detectors designed to capture faint signals from these interactions are currently being developed and refined. By combining cutting-edge technology with sophisticated simulations, researchers aim to uncover whether neutrinos and dark matter share a deeper connection than previously thought. Understanding this relationship not only enhances our knowledge of dark matter, but also sheds light on the fundamental nature of neutrinos themselves. As we delve further into this enigmatic realm, each discovery brings us closer to unraveling the secrets of the universe's hidden architecture. The interplay between neutrinos and dark matter continues to inspire groundbreaking research, pushing the boundaries of what we know about the cosmos. Building on the fascinating interplay between neutrinos and dark matter, let's now turn our attention to another groundbreaking concept: self-interacting dark matter models. These theories propose that dark matter particles might not only interact with ordinary matter, but also with one another, fundamentally altering our understanding of their behavior. In traditional models, dark matter is considered cold and collisionless, meaning its particles rarely interact with each other or anything else. However, observations of certain galactic phenomena challenge this assumption. For instance, in some colliding galaxy clusters, the distribution of dark matter appears less compact than expected, hinting at interactions within the dark matter itself. This has led scientists to explore the possibility of self-interacting dark matter, where particles exchange energy or momentum during collisions. Self-interacting dark matter models offer a compelling explanation for these discrepancies. If dark matter particles can collide and scatter off one another, it could smooth out dense regions and influence the structure of galaxies on smaller scales. This interaction might also resolve puzzles like the core cusp problem, where simulations predict overly dense cores in dwarf galaxies, while observations reveal more uniform distributions. Interestingly, two complementary approaches emerge when studying self-interacting dark matter. The first involves short-range forces mediated by hypothetical particles, creating a kind of dark force that governs interactions within the dark sector. The second considers long-range interactions, potentially tied to existing fundamental forces or entirely new physics. Both perspectives enrich our understanding of how dark matter shapes the universe's architecture. By refining simulations and analyzing data from telescopes and particle detectors, researchers continue to test these models against real-world observations. Each discovery brings us closer to uncovering whether dark matter's secrets lie not just in its existence, but in its intricate internal dynamics. As we delve deeper into this realm, the possibilities grow ever more intriguing, inviting us to rethink the very fabric of the cosmos. Shifting our focus now to one of the most awe-inspiring aspects of dark matter research, let's explore the hunt for dark matter filaments. These vast cosmic threads are believed to connect galaxy clusters across the universe, forming an intricate web-like structure that underpins the large-scale organization of everything we see in the night sky. Detecting these elusive filaments is no easy feat. Unlike stars or galaxies, which emit light and can be directly observed, dark matter interacts only through gravity, making it invisible to traditional telescopes. However, scientists have devised ingenious methods to trace its presence. One of the primary tools in this endeavor is gravitational lensing, a phenomenon where massive structures like galaxy clusters bend light from distant objects behind them. By carefully analyzing distortions in the shapes of background galaxies, researchers can infer the distribution of dark matter along these filaments. Advanced simulations also play a crucial role in mapping these cosmic highways. Using powerful supercomputers, astronomers model the evolution of the universe from its earliest moments to the present day. These models predict how dark matter should clump together over time, forming dense nodes at galaxy clusters and thinner strands, the filaments between them. Comparing these predictions with observational data helps refine our understanding of both the filaments themselves and the broader cosmic web they create. Recent breakthroughs have brought us closer than ever to visualizing these mysterious structures. For instance, the discovery of a luminous bridge of hot gas between two galaxy clusters provided indirect evidence of a dark matter filament. While the gas itself isn't dark matter, its presence aligns perfectly with what simulations predict about filament locations, offering tantalizing clues about their existence. As technology continues to advance, new instruments such as the James Webb Space Telescope and ground-based observatories equipped with cutting-edge lenses will further enhance our ability to map these cosmic features. Each step forward brings us one step closer to unraveling the secrets of the universe's hidden skeleton, revealing how dark matter shapes the grand architecture of space. Primordial black holes as dark matter candidates present an intriguing and somewhat controversial possibility in the cosmic puzzle. Let's turn our attention now to this fascinating theory, which suggests that some of the universe's missing mass could be hidden within these ancient, compact objects. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the chaotic moments following the Big Bang. These hypothetical entities would span a wide range of sizes, from smaller than an atom to many times the mass of our Sun. What makes them particularly interesting is their potential to account for a significant portion, or perhaps all, of the dark matter in the universe. The concept relies on the idea that density fluctuations in the early universe might have been extreme enough to cause certain regions to collapse into black holes almost instantly. If this hypothesis holds true, these black holes would have been around long before the first stars and galaxies formed, quietly influencing the evolution of the cosmos through their gravitational pull. Scientists are actively searching for evidence of primordial black holes by observing phenomena like microlensing events. When a compact object like a primordial black hole passes between Earth and a distant star, its gravity can temporarily magnify the light from that star, creating a detectable signature. So far, no conclusive proof has emerged, but ongoing experiments and observations continue to refine our understanding of what these elusive objects might look like and how common they could be. What's especially captivating about this theory is its ability to bridge two major mysteries: dark matter and black holes. By considering primordial black holes as part of the solution, we may uncover not only where dark matter resides, but also deepen our knowledge of the conditions present during the universe's infancy. As research progresses, each new discovery brings us closer to unraveling whether these ancient relics truly hold the key to one of astronomy's greatest enigmas. This leads us naturally into exploring another tantalizing aspect of dark matter: ultra-diffuse galaxies, where dark matter seems to dominate even more dramatically than in typical galaxies. But let's dive into that next. Let's shift our focus now to one of the most speculative yet fascinating ideas in the realm of dark matter research: action stars. Imagine a form of dark matter so unique that it doesn't just exist as invisible particles scattered throughout the universe, but can clump together into dense, stable structures resembling compact objects like neutron stars or black holes. These hypothetical entities are known as action stars, and they represent an entirely new way of thinking about how dark matter might behave. Actions are theoretical particles proposed as candidates for dark matter due to their incredibly low mass and weak interactions with ordinary matter. Under certain conditions, these particles could condense into Bose-Einstein condensates, states where large numbers of bosons occupy the same quantum state. When this happens, actions could form ultra-dense concentrations, creating what scientists call action stars. These objects would be vastly different from traditional stars since they wouldn't emit light or heat, instead existing purely as coherent collections of dark matter particles. What makes action stars particularly intriguing is their potential range of sizes. Some models suggest they could be as small as Earth or as massive as several suns, depending on the properties of actions themselves. If such objects exist, they could help explain some of the mysteries surrounding dark matter's distribution and influence on galaxy formation. For instance, action stars might contribute to the observed substructure within dark matter halos, affecting everything from star formation rates to gravitational lensing patterns. The concept of action stars also opens up exciting possibilities for detection. While direct observation remains challenging given their invisibility, researchers propose looking for indirect signatures. For example, if an action star were to pass near a neutron star or black hole, its gravitational pull could create detectable disturbances in spacetime, potentially observable through phenomena like pulsar timing arrays or gravitational waves. Additionally, collisions between action stars and other astrophysical bodies might release bursts of energy, providing fleeting glimpses of their existence. While still largely theoretical, the idea of action stars challenges us to rethink the nature of dark matter and its role in shaping the cosmos. As experiments continue to refine our understanding of actions, each step forward brings us closer to verifying or disproving this extraordinary hypothesis. And with that, we move deeper into the enigmatic world of dark matter, exploring another layer of its cosmic complexity. Let's now dive deeper into the hunt for action stars, exploring the potential observable signatures that could finally reveal their existence. One of the most promising avenues lies in gravitational wave astronomy, a field that has revolutionized our ability to detect cosmic phenomena invisible to traditional telescopes. When two action stars collide or interact with massive objects like neutron stars or black holes, they might produce ripples in space-time gravitational waves. that advanced detectors such as LIGO and Virgo could pick up. These instruments are already sensitive enough to capture faint signals from distant mergers, so identifying unique patterns linked to action-star interactions remains a tantalizing possibility. Another intriguing approach involves pulsar timing arrays, networks of precisely measured pulsars acting as natural cosmic clocks. If an action star were to pass close to one of these rapidly spinning neutron stars, its gravitational influence could introduce subtle variations in the regular arrival times of the pulses. Such deviations, though minuscule, would serve as indirect evidence of action stars lurking in our galaxy. On top of gravitational effects, there's also the prospect of direct energy release during action star collisions. While actions themselves don't interact strongly with normal matter, high-energy events involving action stars might briefly convert some of their mass into electromagnetic radiation or other forms of detectable energy. This fleeting burst could manifest as gamma rays or X-rays, potentially captured by space-based observatories like Fermi or Chandra. Experimental efforts are further bolstered by theoretical models predicting specific conditions under which action stars might form and stabilize. Researchers use simulations to map out possible parameter spaces, narrowing down where and how we should look for them. For instance, certain scenarios suggest that action stars could exist near galactic centers or within dense globular clusters, making these regions prime targets for future investigations. As technology advances and our understanding grows, the search for action stars continues to push the boundaries of modern astrophysics. Each new observation campaign brings us closer to unraveling the mysteries of dark matter, inching toward a groundbreaking discovery that could redefine our view of the universe. Connections between actions and inflation take us even deeper into the realm of early universe physics, where the boundaries between theory and observation blur. Actions, originally proposed to solve issues in quantum chromodynamics, have emerged as fascinating candidates not only for dark matter, but also as key players in the cosmic inflation scenario. Let's delve into how these tiny particles might be intertwined with one of the most profound events in the history of our universe. Inflation theory suggests that the universe underwent a rapid expansion just fractions of a second after the Big Bang. This exponential growth smoothed out irregularities, setting the stage for the large-scale structure we observe today. However, what drove this inflationary phase remains an open question. Enter actions, which some models propose could serve as inflatons, the hypothetical particles responsible for driving inflation. One intriguing possibility is that actions arise from a field known as the action field, which may have played a dual role in both generating inflation and later contributing to dark matter. During the inflationary epoch, fluctuations in this field could have seeded the density perturbations that eventually led to galaxies and galaxy clusters. As the universe cooled, remnants of the same field might have condensed into actions, forming part of the dark matter population. This connection gains traction through string theory-inspired models, where actions naturally emerge as low-energy excitations of higher dimensional fields. These models predict multiple action-like particles, each potentially influencing different aspects of cosmology. By studying their collective behavior, researchers hope to uncover signatures left behind by these ancient interactions. Modern experiments aim to test these ideas by searching for imprints of actions on cosmic microwave background radiation or large-scale structures. For instance, certain configurations of actions during inflation could leave distinct patterns in primordial gravitational waves, offering another avenue for detection. Space missions like LightBird and ground-based telescopes such as the Simons Observatory are designed to probe these subtle signals, bridging the gap between theory and observation. Exploring the relationship between actions and inflation not only enhances our understanding of dark matter, but also sheds light on the fundamental forces governing the cosmos. It paints a picture of a universe far richer and more interconnected than ever imagined, inviting us to ponder the incredible complexity hidden within its simplest components. With each new discovery, the veil over the mysteries of the early universe lifts slightly, revealing tantalizing glimpses of truth yet to be fully understood. Shifting our focus to the interplay between actions and particles from the Standard Model, we uncover another layer of complexity in the cosmic puzzle. While actions remain elusive dark matter candidates, their potential interactions with familiar particles provide fascinating avenues for exploration. To understand this connection, let's delve into how actions might influence and be influenced by the fundamental building blocks of our universe. Actions are theorized to couple very weakly with photons, electrons, and quarks, among other Standard Model particles. This feeble interaction makes them difficult to detect directly, but also hints at their role as a bridge between the visible and invisible realms of the cosmos. One intriguing possibility is that actions can convert into photons under strong magnetic fields, offering a potential signature for experimental detection. Facilities like ADAM's Axion Dark Matter Experiment and CERN Axion Solar Telescope aim to exploit this property by searching for faint radio signals produced when actions interact within Earth-based detectors. Moreover, actions could play a pivotal role in nuclear processes. Some theories suggest they contribute to proton decay or modify neutron interactions in ways detectable through precision experiments. These subtle effects, though challenging to measure, would provide critical evidence linking actions to known physics. Interestingly, astrophysical observations offer additional clues. For instance, stellar evolution models predict that actions could drain energy from stars, affecting their lifespans and luminosities. By comparing theoretical predictions with actual star behavior, scientists hope to infer the presence of actions indirectly. Similarly, solar actions produced in the Sun's core might leave imprints on cosmic neutrino streams, providing further opportunities for discovery. This interplay extends beyond individual particles, touching the fabric of quantum mechanics itself. Actions may influence vacuum polarization, altering electromagnetic properties at microscopic scales. Such phenomena challenge our understanding of particle interactions and open doors to new physics beyond the Standard Model. In summary, the relationship between actions and Standard Model particles reveals a rich tapestry of possibilities. Each observation, experiment, and calculation brings us closer to unraveling these mysteries, reinforcing the profound interconnectedness of all cosmic elements. As research progresses, the lines between theory and reality continue to blur, inviting us to embrace the wonders of an ever-expanding scientific frontier. To wrap up our journey through the 25 mysteries of the cosmic dark matter era, let's take a moment to reflect on the profound questions and tantalizing answers we've uncovered. From the elusive nature of dark matter itself to its influence on galaxy rotation, large-scale structure formation, and gravitational lensing effects, each mystery adds another piece to the intricate puzzle of our universe. The subtle irregularities in the cosmic microwave background radiation provide crucial clues about early interactions between dark matter and ordinary matter, while phenomena like missing baryonic matter and dwarf galaxy dynamics deepen the complexity of this cosmic enigma. As we ventured further into the realm of theoretical particles, Axions and WIMP emerged as leading candidates for dark matter constituents, sparking groundbreaking research efforts worldwide. Phase transitions in the early universe, galactic halo properties, and potential dark matter annihilation signals highlight the dynamic interplay between visible and invisible forces shaping cosmic evolution. Alternative gravity theories such as MUND and TVS challenge conventional wisdom, inviting us to reconsider established paradigms. The role of dark matter in supermassive black hole seeds, ultra-diffuse galaxies, and substructure formations opens new avenues for exploration. Meanwhile, speculative concepts like dark matter filaments, primordial black holes, and action stars expand our imagination, pushing the boundaries of what we think is possible. Connections between actions and inflation theories, along with their interplay with standard model particles, underscore the intricate web connecting all elements of the cosmos. While significant progress has been made, much remains unknown. Ongoing research initiatives continue to unravel these mysteries, revealing ever more intricate layers of understanding. As scientists delve deeper into the heart of dark matter's enigmatic nature, they invite us all to ponder the profound implications of discoveries yet to come. What secrets does the universe still hold, and how will humanity's relentless pursuit of knowledge transform our understanding of existence itself? Thank you for joining this fascinating exploration. There has never been a better time to be curious about the cosmos. If you enjoyed this deep dive into the mysteries of dark matter, don't forget to subscribe, hit that notification bell, and share your thoughts in the comments below. Together, let's continue exploring the wonders of our universe. With our exploration of the cosmic dark matter era now reaching its conclusion, let's take a moment to reflect on the incredible journey we've shared. Each mystery we've uncovered has not only deepened our understanding, but also sparked curiosity about what lies ahead in the universe's vast expanse. The questions we've asked and the answers we've begun to piece together reveal just how interconnected everything is, from the smallest particles to the largest structures in space. As you continue your own quest for knowledge, remember that the wonders of the cosmos are open to everyone. Whether you're an avid astrophysics enthusiast or simply someone who marvels at the night sky, there's always more to discover. Your curiosity can lead to new insights and inspire others around you. So why not dive deeper, explore additional resources, read up on the latest research, and join online communities where passionate minds gather to discuss these mysteries. And most importantly, stay connected with us here. If you enjoyed this deep dive into the mysteries of dark matter, be sure to hit that subscribe button and enable notifications so you never miss out on future episodes. Share your thoughts, questions, and favorite parts of today's video in the comments below. We'd love to hear from you. Together, we can keep exploring the wonders of our universe, one mystery at a time. Thank you for joining me on this incredible adventure, and I'll see you in the next video.